Okay, so we left off, we were going to do 12.5 divided by 0.05. So x, we get 250 grams of solution. So for this particular compound, right, we have, because it's 5% solution, 5% of 250 is 12.5 grams. Oh, for sig figs, let me take a look. So we have, remember, we don't look at percentage, so we have 3. So actually, I'm going to have to add a decimal. Or if you don't want to do that, you can always put this in scientific notation. Remember, by adding this decimal, we're giving significance to this 0. Or we can say 2.50 times 10 to the 2 grams. These mean exactly the same thing. Okay, so those are all percentage concentrations. So very low concentrations or dilute concentrations, this is what I was talking about before with the environmental or health studies. So parts per concentration are essentially looking at either mass in volume or mass in mass. Okay, so the ratio here is what's different. Remember, we're looking at very, very small quantities of solute. So parts per million, 1 part per million translates into one of 2 ratios. So either 1 milligram for every liter, depending on if you're dealing with a liquid solution, or 1 milligram per kilogram of solution. So it depends on what you're given for the ratio here. A parts per billion is essentially 1/1000th of a part per million. So basically it takes 1,000 parts per billion to equal 1 part per million. So essentially it's getting into an even smaller concentration. And then we have a term called parts per trillion that's even smaller than that. So the solute amount is getting so smaller and smaller. So 1 part per trillion is essentially 1,000th of a part per billion. So it would take 1,000 parts per trillion to equal out to 1 part per billion. Okay, so very, very, very tiny. So typically when you're dealing with these types of questions, you have parts per million, or you'd have to solve for parts per million first, and then you would basically convert to, so let's say you're asked for parts per billion after, you would then basically convert that. Okay, and I'm going to show you in an example how you would go about doing that. Okay, so we have here a 1.553 sample of pond water is found to contain 1.7 times 10 to the negative 4 grams of phosphates. Okay, so phosphates is our solute. The pond water is our solution. What is the concentration of phosphates in parts per million? And then again in parts per billion. Okay, so remember the key to all this is the units. So we're dealing with either milligrams per liter or milligrams per kilogram. So in this case, because we have a mass of our solute, parts per million that we're going to be looking at here is going to be the mass of the solute in milligrams over the mass of the solution in kilograms, right? So concentration, no matter what type it is, it's always solute over solution. It's just in this case, we're dealing with milligrams per kilogram, which is going to give us our concentration in ppm. So our concentration in ppm is going to be our, oh, pardon me, we have to do our conversions. I just finished talking about that and then we didn't do it. Okay, so the mass of our solute is 1.7 times 10 to the negative 4 grams, but we need this in milligrams. So for every 1 gram, there are 1,000 milligrams. So go back to your unit conversion if you don't recall that. So we have 1.7 times 10 to the negative 4 times 1,000. So we get here 0.17 milligrams. And the mass of our solution, we have it as 155.3 grams, but we need this in kilograms. So for every 1 kilogram, there are 1,000 grams. Right? So we're going to have here 155.3 essentially divided by 1,000, so 0.1553 kilograms. Now that we have this in the appropriate units, we can plug this in for parts per million. So we have 0.17 milligrams over 0.1553 kilograms. So 0.17 divided by 0.1553. So we get here 1.0947 parts per million, and that is the actual unit for this. And for sig figs, we have 4 versus 2. So for 2, we can have 1.1 parts per million. Okay, so now the second part is to solve for parts per billion. So really we're taking our value, and remember, anytime you're continuing forward, you don't want to use your significant digit value, you use your original number, and that's always, in any case, in any calculation. So we have 1.0947 parts per million, and we know in every 1 part per million, there is 1,000 parts per billion. So we're going to take this and we're going to essentially multiply by 1,000. So we have 109.4.7 parts per billion. And then for sig figs, it would still be 2 because we're dealing with the same original data. So it would be 1,100 parts per billion. Ooh. Okay. So actually, oh, I have another one for you to try. I was going to let you try this next one out. So we'll do one more together. Okay, so we have here a study reported that seabirds containing 25 parts per billion of pesticide. What mass of pesticide would be present in a 4.0 kilogram seabird? So essentially we're looking at the bird itself. I know it's funny to kind of say, but the bird is our solution because we're looking to see how much of this pesticide has made its way into the bird. So if you remember from grade 9 ecology, this is kind of like we're looking at the bioaccumulation of a pesticide. So the first thing we're going to do, so our concentration is 25 parts per billion. So we're going to convert that into parts per million first so we can actually deal with it in the proper units. So 1 part per million is equal to 1,000 parts per billion. So we end up getting 0.025 parts per million. So remember that parts per million is either milligrams per liter or milligrams per kilogram. Those are the two options depending on what you're given. So here we have a solution that's in kilograms, so we're going to be using our milligram per kilogram ratio, right? So parts per million is essentially going to be the mass of your solute over the mass of your solution. Just want to make sure your units are proper. So we have 0.025 parts per million is equal to, so we're given our mass of the pesticides, what we want. So we're looking for the solute, and we have here that we have a 4.0 kilogram bird. So to solve for x, we're going to multiply those two values out. So we get 0.025 times 4, which gives us 0.1. And that's going to be in milligrams. So remember our ratio for parts per million. And for sig figs, it's going to be 2. So actually we have to add on a 0. Okay. So give this next one a try. So we have dissolved oxygen in water is an important measure of an ecosystem's health. In 250 milliliters of water, we have 0.022 grams of oxygen. What is the concentration in parts per million? So pause the video, give this a try. All right, so let's take a look at what we have here. So the volume of our solution is 250 milliliters. So remember, so in this case now we're actually going to be dealing with parts per million in milligrams per liter, since we're dealing with a solution in volume measurements. So we need this in liters. Okay, so the mass of our solute in this case is oxygen. We have 0.022 grams, and we're going to convert that into milligrams. So for every 1 gram, we have 1,000 milligrams, which ends up being 22 milligrams. Okay, so now that we have it in the proper amounts, we can solve for concentration in parts per million. So it's going to be our 22 milligrams over 0.250 liters. And that ends up being 88 parts per million. And we need 2 sig figs. So actually that is already in the proper amount. So really any of these concentrations, it's always the same thing. It's solute over solution. But it depends on your units. They've never been more, they're always important, but especially when you're dealing with concentration, you can't just take your solute and divide it by your solution. Your values are going to be wrong. Okay, so to make a summary, let's look at the different types of solutions and what the units would be. So your solute and your solution and your, hold on a second. Okay. So let's say our concentration type. So we'll start off with the one that we began learning about. So let's say we had molar concentration. And let's do our units for concentration as well. So the solute has to be moles. The solution has to be liters. So the concentration for our units, our unit concentration actually is going to be moles per liter, right? So then we looked at percent. We started with volume and volume. So this has to be milliliters, milliliters, and your unit really is just percent V/V. So percent W/V, we have grams per milliliter, which is percent W/V. Then we have percent WW, grams and grams. I feel like this last column is really only important for this one. The other ones are pretty much the same. And then we have, of course, parts per million. So there are 2 types. I'm going to have both of these for that. So you can have milligrams per liter. So the unit is parts per million. Or you can have milligrams per kilogram. The unit is still, of course, parts per million. So all of these are solute over solution, okay? But how they're expressed, what your information you're given, what you're asked to solve for can be very different. So anytime it says, calculate the concentration, you have to stop and think, okay, well, what type of concentration? What are the units I currently have? What do I need in order to solve for this properly?